Hello everyone, welcome back. So this video is kind of a reflection video talking about the process and my thoughts for the design of async awaits in the Microvium JavaScript engine. If you don't know what that is or don't know what I'm talking about, go back and watch the first video or read my blog posts, which I've linked in the description. I'll just be assuming in this video that you're familiar with what I'm talking about. As with the last video, this is unscripted and informal, so expect it to be a little bit rambly and informal. So let's share. So let me first show you behind the scenes of the process itself. So here I have, this is a private repository that I use for recording my thoughts, which is mostly design thinking about various things in Microvium. I'll do this for all my projects, but this is for Microvium. And you can see here it goes right back to near the beginning of Microvium in 2020, and I've just got like tons and tons of markdown files. Whenever I either have an idea or I want to iterate on a process or iterate on a feature, iterate on a design, I'll drop in a note, a document here. Let's say, okay, exceptions revisited. I'll pick a random one to give an example. So I was thinking about implementing JSON parse as a library, but then realized that library functions need a way to communicate errors to the caller, so we need exceptions. Okay, so this is 2022. I wonder how difficult it would be to add. So actually, I did implement. I forgot that I implemented exceptions that recently. Wow, that's cool. Okay. Anyway, I thought it was like it's been in the engine for longer, but actually, it's been quite a recent addition. So, so there's an example, and I have a whole history of this. So it's probably exceptions revisited because very likely, there we go. Almost a year prior, I have thoughts about how exceptions might be implemented in terms of long jump and set jump. That's not how they implement it in the end, but that was my first pass at it. Anyway, we're here to talk about async await. So let's go here, async. So where's the first one is here. So you can see on the left here, I've got quite a few thought documents, whatever you want to call them, on async await, which kind of shows like how the process unfolded. So starting in May 2022, and as I'm recording this, it's beginning of November 2023. So that's over a year ago. So that's kind of when I first started thinking about it, or probably around the first time I started thinking about it. So let's look at the process here. I said I did a recent post on my blog about how great Microvium is for controlling asynchronous logic because it has closures. But of course, one thing that would make it even better would be async await. So I said even more useful than classes, but definitely classes got into Microvium before async await. So yeah, so this was kind of the first take on it. If I recall, yeah. So after thinking about it further, I definitely think that the lowering approach, so lowering lowering the syntax into like a transpiler, essentially using like Babel or transpiler or something. Lowering approach is probably the best approach. I did change my mind on that clearly, because now it's definitely not using a lowering approach. But this kind of shows the process of like, okay, I think this is the way to go. And then that was May, and then I let it simmer for a bit. And then, in July, August, whatever, I started thinking about it differently. So thinking lowering approach is the best approach. I found a transpiler Babel plugin, compiled some code with it, and then it's like, okay, so I won't be using this plugin directly. Why? Okay, because when I introduce the loop, it becomes substantially more complicated, requiring a ream of additional helper functions, which are quite big. So the cost of using a transpiler was just ridiculous. I don't remember the exact, this is a long time ago, but here are some of the helper methods that it generates. But I remember it generating pages and pages of scripts, and the code that you write, it doesn't look anything like it by the time it's transpiled. It's substantially more verbose. So then I took a first pass, I guess. I can't remember. Then looking at it again. So July, I came back to it, had some more ideas about Okay, so I thought async is more important. I won't go through the whole process, by the way. This video, it'll be a pretty boring video if we do that. But I wanted to kind of at least show how at a high level what it looks like. So some more ideas. Here's kind of the first one where I said, okay, I know I have something that I actually want to propose. So I was going to post this as a GitHub issue. I did post a proposal as a GitHub issue. It was like an iteration on this, I think, or probably was. But anyway, here was kind of the first iteration of a proper proposal. I said, okay, we've got a new register because we've got to have the queue. Whatever, opcode to add to queue, library changes, we got promises, examinables, identifying promises using a special property. It is promise is true, which is kind of hacky, but it was a first pass at it. And then some actual code here, sort of brainstorming what a promise might look like. We didn't have classes at the time. I say we, Microvium didn't have promises. Didn't have classes. I'm the only one working on it. So promise. So I was thinking, okay, I'm gonna have a function to create it. Code, compiler changes. Okay, this is the proposal. Blah 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 blah, and then kind of the summary here. Let's see. Edit engine size is quite small. The promise queue, I expect it was much more expensive in the end, 100 to 200 bytes of ROM to Microvium size. That's very optimistic, or maybe in this particular proposal, that's what it is. But in the end, I don't even know, man. Maybe it added maybe 2 kilobytes of size to Microvium, given that it was only 10 kilobytes. That's quite a lot. So the interesting thing I noted here that I wanted to show is that here's kind of the add up of how much memory it would use for a minimal suspended async function, and that's a total. It adds up to the total of 80 bytes, which is, well, that it's actually probably smaller than than any other JavaScript engine, but it's still ridiculously large compared to what it is in the final version. So you can see here I kind of iterate. This is my process. Async await continued, and then refining the engine changer. And then, okay, simplifying. You can see here, minimal async, simplifying async, revisiting async. It's like, these are long documents, right? Each one is kind of a refinement and an iteration, where I kind of just use the previous documents as inspiration rather than like, I leave them there because I may want to refer back to them or look at the process that I went through or whatever. It's useful. But for the most part, I just like try and think blank slate, like not always blank slate, but oh here, look, in the last doc, I fleshed out the design for async and it came out to 80 bytes. That seems a bit excessive, so I want to rethink it from the ground up in terms of a minimalistic design. I'm curious what the conclusion was here. 30 bytes. So the second iteration where I'm like, okay, can I shrink this down? Can I just, what's minimal? What's the least I can do? And I got it down to 30 bytes. And then that's quite far from the 6 bytes. That it is now, but you can see the direction that it's moving. And this I think is important, like for a feature like async await and perhaps many other features I've worked on, I find it's much better to not to start on it right before you want it to be done. I mean, of course, you always want it to be done right after you've started it. That would be nice. But you got to give it time to simmer. You got to give it time to for your subconscious processes to work through some of the issues. You got to give it time to brainstorm and come up with alternatives. Your mind will be in different states each time you approach the problem. And you'll remember key insights from the previous documents, like the key things that stood out as like, that we can reduce it by doing this, we can do this, this is a clever or elegant way of doing it. You'll remember those things, but when you're doing another iteration, you'll remember those things and come up with new things, because you're in a different state, because you watched some other video on YouTube recently that was different, that like triggered some pattern or whatever. Like you're getting other informational content into your brain. And I think like this, so I wasn't like committed right from the beginning to say, okay, I have a proposal, let me go and implement it. And that's normally what you do when you're in like a business environment, like for my day job. You're asked to design something and then implement it. There's very little space for just saying, here's an idea, I'm going to come back to it in 3 months' time and refine it. And then I'm going to come back to it in another month's time and refine it. Or just refining it multiple times, even, like refining ideas, at least in all the companies I've worked in, is not a thing. It's not a legitimate piece of work. If you go to your stand-up meeting or whatever, or your progress update, and you say, well, what did I do last week? I took an idea that I had and I now have a clearer idea, or I have a improved idea. Like, yeah, nobody's paying you for that. But if you look at something like async await, is a great example of how valuable that can be, that you can, in a sense, after multiple iterations here, I really refined it down to that kind of bare essence. And this end result here is I'm really happy with it. So it worked out well, and maybe that's a good segue to transition into like my thoughts about the overall process, my thoughts about how it turned out. So this way of doing async await, as I mentioned in the previous video, is quite different to what other JavaScript engines do. At least to my knowledge. I could be mistaken there. And certainly it's quite different to how the ECMAScript specification presents async await. It's all in terms of promises and what have you. But then if you think about how the ECMAScript specification represents function parameters, for example, as being, there's this kind of what is it? I'm trying to remember. But you can iterate the parameters, and basically when you pass arguments, when those arguments are resolved to parameters, then that's done by creating like a parameter iterator object in the spec. But of course no engines actually do that, because 90% of the time that iterator object is completely invisible to the user. And that's kind of what I'm working off here, is that in an example like this, the promises are completely invisible to the user. They're not always, but a lot of the time you're going to be writing code like this where you don't want promises. Promises are they add complexity to your code that you don't often need. So you're often going to be doing this kind of simple awaiting a function call, and in that case you can elide the promise altogether. So it's kind of, in some ways, it's experimental. It's not experimental in the sense that, like, through the iterations I was pretty confident that it would work. I wasn't testing it out, and came to the end of the process and I'm like, yeah, that worked. So yeah, of course, the callback system makes sense. The hard part, well, there are many hard parts in this, but the one of the hard parts is this the CPS handshake. Where is it? This handshake, right? It's reasonably simple as presented here, but this took multiple iterations of design thinking to come up with a way to support promises alongside callbacks. So, like, you gotta be able to create promises when they're required, and it wasn't obvious. At least it wasn't obvious to me. In the first iteration, and it gets so confusing when you're trying to solve that at the same time as solving all these other problems as well. Anyway, so I think I may go out on a limb and say I think this is kind of groundbreaking, and certainly someone's probably going to comment and say, no, it's not groundbreaking. Some such and such engine already does this. Sure, yeah, but it's groundbreaking as far as I know. And I'm just scrolling mindlessly while I'm talking. Let me try and pause my thinking while I'm hold on. Oh yeah, okay, this is what I wanted to look at. So it's being able to represent an async function, a suspended async function, in 6 bytes of memory plus your additional user defined state, but 6 bytes of kind of core state. That's like this is what the engine requires to do its job. That completely, to me, changes the way you can use async await. As an embedded programmer, like if I'm faced with async await that requires 50 bytes or 100 bytes or 420 bytes or whatever of memory. Like, I'm going to be very hesitant to use async await, and I might use it in the very highest level workflows where there may be only one workflow or two workflows across the whole the whole program, and then maybe you only have one suspended function, because it's a, if you're paying 100 plus bytes for a suspended function, it's like that's really expensive. And not to mention, like, if you want to have a dedicated RTOS thread or something, that could be a couple hundred bytes of stack space. So it's kind of like, if your async functions, if you just got like this example here, you've only got 3 levels of async functions, and if each one is taking 100, 200 bytes, let's say 200, because I'm going to guess that that's quite common for embedded JavaScript engines. If it's 200 bytes, you've got a 600 byte structure here without any detail, before you've added any variables. Then you might as well just do it in C, do it in C++, and have it on RTOS thread. 600 bytes you can do a lot with, and an RTOS thread will give you the ergonomics of async await. Not completely, but yeah. Anyway, so so the size, and yeah, I had to reduce the size of closures even to make this possible, and reduce the design of closures to make the function pointer mutable, so that I could use closures for async await. There are multiple steps to get to this tiny size, and yeah, the end result is that it makes it, I think, even better than C and C++ in terms of memory efficiency. If you're running on like let's say an ARM processor, small, like ARM Cortex M0 is what I often look at as my canonical Microvium processor. It's a 32-bit processor. Two words in C, 2 pointers or something in C are going to be 8 bytes already. So this representation in Microvium is even more compact than 2 words. And Microvium in a 32-bit machine will still be running using 16-bit slot size. So it gives you another level of efficiency, to the point where if you translate your C code to JavaScript, it might become more memory efficient than the equivalent C code. Depending on how you implement it, of course. If you pay a lot of attention to your memory in C, you can do better, of course. But kind of a naive implementation. Anyway, so I'm really pleased with the way it turned out. So you've seen my process. I've talked a little bit about my overall thoughts on it. I think, the other thing I'll say is that taking a year, it took over a year, and I sort of branched out. I created the Git branch, I don't know, maybe a year ago. It's a long time to maintain a side branch, especially when you're a single person working on it. At least it does help that I was the only person working on both, on the main branch and the side branch. But there was other major advancements on the main branch at the same time, changes to support the WASM build of Microvium and things like that. It's demoralizing going for so long. And I always hope for these things to be faster. I'm always more optimistic about how long it will take. and then it just keeps going and going. At the beginning of the year, like January, I'm like, oh, I'm so glad I'm almost finished this. And then like it was September, October. Was it September? I can't remember if I released in September or October, but it's like in January, I'm like, oh, it's almost finished. And then it just keeps going. And there's always like, oh, there's that little thing I didn't think of, the little um, interaction with one of the other features or something, like, oh, I didn't think about how to allocate, how do you, when you have nested closures inside async functions and they've got to access variables in the async function, but the size of the async closure is determined by the number of temporaries, and the temporaries are determined by the stack depth at the await points. And it's just things you don't think of. Yeah, it always takes longer than you think. Anyway, but I got to the end of it, and I'm glad to have merged it all unit test passing. I'm glad I've got extensive unit test coverage, and overall, I think it's been a reasonable success. Did I say? I think I said in the last video that like if you're watching this and you are and you're working on an engine, on a JavaScript engine, or for that matter any other engine that might have async await, and you want to use a similar Design, you can go ahead and use this design. It's all open source. It's MIT licensed. It would be nice if you let me know and maybe acknowledge me for the inspiration of the design. I'm sure in a different JavaScript engine it'll be a different design. And feel free to reach out if you want any more details about how I implemented it. Yeah. Anyway, so I'm happy with how it turned out. It's definitely a feature I will be using in my next firmware project. I can see it being useful in many different use cases, and it opens the door for like some really elegant ergonomic code for all sorts of things, server communication and what have you. Anyway, I hope this video has been useful, and I hope you got something out of it. I'm imagining it's quite a small audience that's interested in this, but good for you if you've gotten this far. Okay, thanks. I'll see you again next time.